Now in this short video I'm going to show how you can use calculus to relate the position, velocity, and acceleration functions that describe a simple harmonic oscillator. I'm going to count on you knowing a little bit of calculus to be able to follow along. Well, we're going to need some sort of starting point for our functions, and so I'm going to imagine we go back to the laboratory and we set up a simple harmonic oscillator, just something like a mass hanging on a spring, or maybe we put it on a horizontal surface, a frictionless surface, and we put a little motion sensor up to it, and we just get a plot of the position as a function of time. Now we can get a lot of things happening here depending on where we start things, but you're bound to get something that looks a little bit like that. And that should be a function that you recognize as either some form of sine or cosine function. The traditional way we write this function is the position as a function of time. Of course, we have some what we call the amplitude. That's the maximum value up here or the lowest minimum value down here. And I'm going to indicate that by x max. This is the way the AP reference sheet writes it. Other times you'll see that written as an A for amplitude. And then we use a cosine function traditionally. You don't have to, but our book doesn't. We'll do it this way. And inside the argument of the cosine function is a quantity that says omega t plus phi. A couple Greek letters in there. Omega represents what we call the angular frequency of our system, and the phi represents what we call the phase shift for the system. The phase shift is actually not a very important number. It just is determined by when exactly you start the timer for your simple harmonic oscillator. The easiest thing to do is what I did here. You start the timer at time equals 0 when the function is at the very highest positive position, and then you actually don't need a phase shift number for the cosine function. So that's what the position function looks like. So if we start with that, then we're going to review a little calculus here, and remember that a velocity function can be found by taking the derivative, the first derivative of the position function with respect to time. We write it dx dt. So I'm going to count on you knowing some of your basic derivatives for trig functions. And the most important one here is the derivative of a cosine function is a negative sine function. We also are going to employ the chain rule here because we're taking a function that doesn't have just t in it, but it has a function of t, just an omega t. So the chain rule says that when we're all done with taking the derivative of the cosine function, we're going to also take the derivative of the omega t with respect to time, and we're going to include that quantity in there too. So here's what we're going to end up with for our velocity function. I'll write it in red. The chain rule is going to put an omega out here in front, and then we're also going to have a negative sign because the derivative of cosine is a negative sign. I like to put that out in front. So we'll have an omega times x max times the sine of, and then the argument is going to be the same, omega t plus phi. So there's the process of doing the first derivative. And then to get the acceleration function, we do the same thing over again. But this time, acceleration is just the derivative of velocity with respect to time. So now you have to know that the derivative of a sine is a cosine. So the acceleration function as a function of time can be written. It'll still have a negative because we don't have anything to change the sign. The chain rule is going to introduce another omega. So we're going to have an omega squared. Then everything else will look pretty much the same. We got the maximum position, called the amplitude. Now we're back to a cosine function whose argument is still omega t plus phi. And so there we have all three functions. Now a couple of things I'll point out here and maybe circle them for your attention is each of these functions also has what we call an amplitude. So this coefficient out here is called the velocity amplitude, and we can determine the maximum velocity of our system if we know omega and the maximum position. And then here we have the acceleration amplitude, or the maximum acceleration our system can have. That's omega squared times the position amplitude. The omega number is pretty important. I think I'll emphasize something about that. That's a characteristic that determines the timing of your oscillator. You know, some oscillators move very rapidly back and forth, and some not so rapidly. And so that omega number built into that is what we call the angular frequency, and that is related to the more familiar frequency, which is just the number of oscillations per second. That's what we call F, oscillations per second. When we multiply that by 2 pi, then we get the angular frequency. It's important that we have the angular frequency inside the cosine and sine functions so that they will repeat themselves at the appropriate time, because a traditional sine and cosine without any omega in there would go, one period would be 2 pi. So that's the reason for the 2 pi on there. The phase shift, as I mentioned before, I'm going to have a separate video about that, is determined basically by when you start the timer, where your oscillator is in its cycle. So I'm not going to say much about that right now. I think I might leave it at this here because I've shown you what I want to show you with the calculus, and anything more than that you'll have to see me or find another resource to maybe amplify this a little bit. Hopefully this was enough to kind of help you understand where these functions come from.